say 10 buckets, right? Right. So those with that, let's say you're sorting on digit position 1. Okay, those with values 0 in the digit position 1 will go into this bucket. Those with the value 1 in that digit position will go into this bucket, and so on. Right? So you scan all the numbers in that digit position and drop them into the right bucket. Okay. Note that in this case, because there is exactly one value, right, no further sorting is required, right, because everything is already in that order. So for instance, let's take let's take right. So let's say that is a sequence that we want to sort. Let's say for the moment we are only dealing with numbers with single digits. Okay, then we'll go to the numbers with multiple digits. Okay, so you see number 1, well, that goes into this bucket. Number 2, so that goes into this bucket. Then another number 1, so that goes into this bucket, right? And then one more number 1 that goes into this bucket. And then 4, 5, and 7. Right? Now, what I'm trying to say is that within each bucket, things are already sorted because there's exactly one value. Right? So because there's only one value, well, by that you don't have to do any more work. It's already sorted because it's just a one value. So all you need to do is concatenate the bucket contents, right? And then you're done. Okay, so this is what is called, counting sort. Okay, counting sort means the bucket contains only one possible value. Therefore, once you put them in the right bucket, you finish sorting already. Okay, so now we see how this works for single-digit numbers, right? So, but of course that's not very interesting. So what do we do when we have, multiple digits? What we do is we sort on the first digit, and then we use the same technique to sort on the second digit, and so on. Okay? So let's see how that works. So when you say first, then the natural question is, are we talking about first from the right or first from the left? Okay? So LSD sorting means you first sort on the least significant digit, and then in successive rounds you go to more significant digits. And MSD sorting, you first sort on the most significant digit and then go to the right. Okay? So let's take an example, and we will see how this works. Okay? Okay, so now let's do this again with 2-digit numbers. Okay? Okay, so let's say we have 5 numbers, okay, and let's say we do LSD sorting, which means that we first put them into buckets. Well, this is not a very good example. Let's change. Okay, let's change 24. Okay. So LSD sorting, we are going to look at the least significant digit and put them into the right bucket. Okay, so we have 0, so 10 goes into that bucket, right? Let's just make this into okay, 40. So then 17, so the least significant digit is 7, so it goes into the bucket 7. 24 goes in here, right? And 14 goes in here, and 34 goes in here. Okay? So at this stage, in one linear scan, right, we have filled all these buckets. Then we can concatenate these elements, right? So after one round, we have the sequence 40, 24, 14, 34, and 17. Right? So we have just concatenated the bin contents. Okay? So far, is it clear, or do you have any questions? Again, all we are doing is we are looking at the least significant digit, putting them into the right bucket, and once we have gone through the scan, we concatenate the bucket contents and we get the result shown there. Okay? So now we have done sorting on the least significant digit, then we just go ahead and do the sorting on the most significant digit. So we form the buckets again. Okay? So we're going to see this number 4. Okay, so 40 goes in here, right? 24, again, remember that last time we were looking at that digit. This time we are looking at the next digit, which happens to be the most significant digit. Okay, so then you have 24, so which is going to go in this. Then 14 is going to go in here. 34 is going to go in here, and 17 is going to go in here. Okay, so we are done. Okay, now we write down, concatenate the contents of the bins. Now we have 14, 17, 24, 34, and 40. Right? So we finished sorting the numbers. Okay? So there is actually a benefit in doing LSD first, and then the LSD sorting has an advantage because, you know, so notice that 17 ended up after 14, right? Because 17 was after 14 because 7 was after 4, right? That's why we got the order in there of 17 occurring after 14, okay? On the other hand, in the first round of sorting, we had these 3 numbers out of order, right? Because they all happen to have the same least significant digit, so they were out of order. But when we did the sorting on the most significant digit, this problem got resolved, and we got them in the right order here, right? But the numbers that were already in the right order, such as 14 and 17, right? That order is not being disturbed because you scan 14 first and put it into this bin. So the 14 will be occurring first in this bin, right? And then you come to 17, then 17 goes into this bin. So the original order in which elements were put into this bin, the original order in which you have the numbers there is preserved among elements that have the same first digit, right? If they don't have the same first digit, then they will be reordered because, well, obviously this is the more significant digit, right? So any number that has a smaller, most significant digit should appear earlier in your sort, right? So that is true. But the point is that among the numbers that have the same first digit, okay, you're going to preserve, the order that was there after the first sort. Okay? So that is Radix sorting, and this way of preserving the order, right, relates to a concept called stable sorting. Okay. So any questions on Radix sorting? Yeah.
Okay. So what if one of the numbers is let's say 5-digit number and rest all are 2-digit numbers?
So that is something that you will do in your homework. Okay. Okay. So let's before we do that, let's make sure that we understand that this is, essentially a linear time algorithm, right? Because if you assume that the number of digits is fixed, right? It's not variable. Once you say that the number of digits is a constant, then you have to do, let's say there are C digits, then you have to go through the C rounds, right? So start from the least significant digit, next significant digit, and so on up to C, right? So you have to do this, one step, do this step C times, okay? And each of those steps requires only linear time, right? So you compare the number, put it into the right bin, right? So you repeat this Cn times, right? So C is the number of digits, and N is the number of elements you want to sort. So in Cn time, you have finished sorting, okay? So how does it relate to the proof that we had before? Right? You cannot do better than n log n, yet we have what looks like an order of n sorting algorithm. So what's
It's not a comparison. We have not compared. We are using the property of the number itself to sort.
so what property are we using? What
The value, face value.
Okay, so you could say, I guess the simplest thing you could say is that you're using a division, right? So although you don't really have to use division in order to use this algorithm, but the simplest way to describe what we are doing here is, we are computing some quotient or modulo operation that tells us which bucket we should put something in, right? So there is no.
The bound doesn't apply.
The bound does not apply because that bound applies when you use only comparison-based. If your algorithm is constrained to use only comparisons, then the bound still is n log n. But if you're allowed to use other operations, then you might be able to sort faster, right? So that's not there is no contradiction between the lower bound proof and the bucket sorting and Radix sorting algorithms. Yes?
So in worst case, it can go up to big of n squared, right? So
Why n squared?
So what if we have n numbers and all are n-digit numbers?
Okay, so the place where Radix sorting is most useful, right, is actually when you deal with strings, okay? Because you can think of strings as, they're a sequence of, so what we call as digits, right, is simply an alphabet consisting of 0 through 9 or whatever, depending on the base, maybe it's 0 and 1, right? So what we call as a digit is set of elements from a finite alphabet, right? So if you think of it that way, a string is nothing but a sequence of elements from a finite alphabet. So you can apply the Radix sorting technique to sort strings, okay? And for numbers, when I say, assume that they have only a constant number of digits, that seems acceptable, right? But if I say strings, and if I say assume that the strings have a constant number of letters, that does not seem very satisfactory, right? So you need to deal with strings which have variable length. So then the question is, how do you do that, right? And what you're alluding to is that if you could say n strings of length at most m, right? Then this simple technique will give you O of nn, right? Because there are m digits, so you got to do this m times, and each Each round takes O of n time. So a simple application of this to sort strings will take order of nm, which is basically like a quadratic type of bound, right? But in fact, you can get an algorithm which is order of okay, let's SI denote the ith string, okay, and that notation
Length of
references the length of that string, and then you sum that, right? So you can think of the length of the string as its size, right? You can't say that the size of the string is a constant. It's not, right? It's proportional to the length. So you can find a sorting algorithm that works in order of the sum of lengths of the string, or in other words, an algorithm that is linear in the size of input. So this is one of your homework problems, and all you need to do is you need to be a little bit, clever about. So the reason why you get an nm is that every string is being considered at each round, right? So you can just go back and say, do I have to consider, what if the string doesn't even have the fifth, character? Do I have to count it in that round, right? You don't have to, right? Because you should be able to do something cleverer. If, let's say, half the strings are of length only 4, right? Then the fifth element you don't have to compare for these strings that don't even have a fifth digit, right? So if you're clever about that, then you'll figure out that yes, I only have to spend time for those strings, on behalf of those strings that actually have that position filled in. Right. So once you do that, then you will quickly get to this algorithm. Any other questions? Okay, so stable sorting. What is stable sorting? Stable sorting means that if two elements are equal, right, then the algorithm doesn't permute their order, right? It doesn't preserves them. It preserves the order of elements that are already sorted, right? So let's say here's an example that kind of shows you where it is useful. Okay, so let's think of sorting cards, right? So you have numbers and suits, right? So you talk about, okay, how do I, I define an ordering that says, let's say, spades is bigger than hearts, is bigger than diamond, is bigger than clubs. Let's say that's how I define the order on the suits. And then maybe and the ordering on the numbers is pretty obvious. So now I want to sort in such a way that the numbers are sorted in the cards are sorted according to both criteria, right? So now so the idea is that you could first sort on so if you sort on, let's say, the suit first, okay? Now, and then you sort on, let's say, the numbers, right? So the idea is that things that are already sorted, if you move them around, right, then your original sorting order might be disturbed, right? So in this case, right, so we already had 17 appearing after 14, right? If in this stage, in the second round of Radix sorting, we preserve this order, then we would end up with the numbers in the right order, right? But if we said, okay, again, if we didn't preserve the order among elements that have equal value, right? Again, remember at the second stage, we are only comparing the first two digits, the first digit, right? So in that sense, these two keys are actually equal, right? So if we mixed up the order of these two keys, right? If we did not preserve their original order, then at the end we would not have this in the sorted order, right? Otherwise we would have 17 and then 14, right? So that wouldn't be sorted, right? So what a stable sorting algorithm allows you to do is you're able to sort in a problem like this. You're able to sort on one of the dimensions, and then you can do the sorting on the other dimension, and then finally what the result that you get is going to be one that is sorted along the combination of the two dimensions, right? So because the sorting that was done in the first stage is not completely, destroyed in the next stage. It is disturbed only to the extent that the comparison, the dimension that you compare in at the second stage, right? If that requires you to rearrange, then you'll rearrange, right? So, for instance, here, 24 and 14 are in this order, right? Now, comparing the first digit 2 and 1, that comparison requires them to be reordered, and you're going to reorder them, okay? But when you deal with numbers like this, which are equal when you do the comparison, then their original order is going to be preserved, and that's how you make sure that at the end you get things to be sorted. So, okay, so many of you have presumably, all of you use the web, and web often has tables, pages with tables, and many times the tables can be sorted, right? So, how many of you have tried to sort on multiple columns? And tell me how that sorting on. So obviously, typically web pages don't allow you to simultaneously say, not unlike, let's say you go to a spreadsheet application, then you can say sort on column 3 and then on column 5 and then on column 7, right? So you can specify the order in which the order of significance of different columns, right? On a typical web page, you have controls that allows you to sort on a particular column without any way to specify whether you can sort on the other columns or not. You can independently sort on each column, but what if you want to sort in a certain way? Have you tried to do that? And if so, have you seen pages where that is possible, and have you seen pages where it's not possible? So let's say you want to sort on column 1 and then on column 2. Okay? And you have a web page that allows you to say, okay, you can click and say sort on column 1. It's sorted on column 1. Now you go click on column 2, and now it's sorted on column 2, right? Now, but do you have any, after you have sorted on column 2, do you know anything about the sorting order on column 1? Okay? So if you use the stable sorting, then you know that the order that you got on sorting the column 1 wouldn't be unnecessarily mangled up, right? So again, think of this like where the first digit is on the first column and the second digit is on the second column, right? So it's a very similar problem, right? So if you have a stable sorting algorithm, then that will keep the original order, right, that you achieved after sorting on one of the columns. So in the end, you can get what you want, right? So now tell me, suppose I sort on column 1 and then column 3 and column 4. Okay? Now, of these, which is the most significant column? Let's say I have, so if I use a stable sorting algorithm, then I can achieve some order of combining those 3 columns by successively, let's say, sorting first on C1 and then sorting on column 3 and then on column 4, right? So which is the most significant column here?
C4?
4.
4, right? Because that is the one that's going to, because this is the one that's performed last, so that's going to have the most significance, right? So, and then this, and then this. So, if you go to, if you import that web page, that table into a spreadsheet, and then you want to achieve the same sorting order, then you would say first sort on C4, and then sort on C3, and then sort on C1, right? So, working back, so that's an example of where stable sorting could be useful, because the interface itself, obviously on a simple web page consisting of tables, one doesn't want to give you this complicated interface that you have on a spreadsheet that says, sort in this, complicated order. But you can, if somebody designing the page was thinking and was implementing the right sorting algorithm, then you would be able to achieve that effect, right? So again, what you will see is that there are some web pages where the people who designed it, had the sense to use a stable sorting algorithm, so you don't have to be frustrated. And there are other pages where somebody uses QuickSort, right? That's the most obvious thing to use. I'll use QuickSort. Well, you use QuickSort. QuickSort is not stable, and therefore, by the time you sort on C3, the order on C1 is no longer there. So you are stuck, and the only thing you can do is sort just on one column. You can never achieve sorting on multiple columns. Okay. So, so again, stable sorting is a very useful concept, and something that I would like all of you to know. So when you design a web page like that, don't make that mistake. Okay. So sorting strings with, I already talked about this. Okay. So easy enough to do order of NL, where L is the maximum length of all the strings, but you want to get something that's linear in the total length of all the strings put together. Okay, so now we will talk about a problem that's related to sorting, which is selection of the kth largest element. Okay. So let's very quickly summarize what we have done so far, right? So we talked about various sorting algorithms. Comparison-based sorting algorithms have an n log n lower bound. By using other techniques, other operations other than comparison, you can get linear time sorting, right? So that's the summary. So now we will branch off to the closely related problem of selecting the kth largest element. Okay? Well, of course, you can. The most obvious way to do it is you sort it, and now you know which is the kth largest or kth smallest element, and you can pick it, right? But obviously, you don't care about the order of sorting the remaining elements. You only only care about the particular element that happens to be in the kth position. You don't care about the rest, right? So, thinking back about this search tree or tree consisting of these permutations, you don't have to get to any one particular leaf, because getting to a leaf means you have resolved all the questions about the relative order of every pair of elements, right? So here, you only want to, resolve the question involving that one element and every other element, right? So you need to only make, if you think in those terms, right? So you only need to make sure that, it is this kth element, right? There are k elements less than that, and the remaining elements are all greater, right? So if you think in the frame of that picture, then you'll see that, well, it looks like I should be able to do this if I knew which comparisons to make, right? If I could guess which comparisons to make, right, then I can do this in linear time, right? So suppose somehow I could guess these are all the elements that are less than, suppose you can guess which is the right element, then you can very easily verify that, okay, somehow k elements are actually less than that and the rest are greater, right? So thinking purely in information theoretic terms, it seems that in a linear number of comparisons you should be able to figure out. So now well, that's just a hunch. So now the question is whether we can actually do this. Okay.